Hello there guys, so today I am back with another video in the Networking Talks video series that I've been doing alongside while I've been working at TechX since I've joined there recently. Today I had a chat about OSPF in some detail, a bit of a technical introduction, however maybe I go in a little bit more detail than just in a technical introduction. While talking with the team, they were saying that I went in a little bit more detail than like CCNA does. So if you're looking for some kind of good resource and good summary video to go over some high-level points, this seems like a good video for you. So feel free to take a watch. Let me know if you spot any issues, let me know if you have any feedback, and let me know if you have any specific topics that you want me to cover. Maybe at some point in the future I'll do a few more of these and I can take on some suggestions. But yeah, anyway, enjoy the video, let me know if you have any feedback, and thanks for watching.
Hello guys, bit of a technical introduction today to OSPF. Similar to the BGP one, we'll talk through a few key points, how it's used, where it's used, the fundamentals, path selections, those kind of things. So without further ado, what can it be used for? At a really high level, key fundamental is that it's used mainly just for internal IP reachability. So there's a few key points there. Internal, so usually used with inside a company, or usually used with inside one location. But there is nothing stopping you using it across multiple different companies, multiple different locations, over the internet if you wanted, if you had the relevant protocols underneath it to run that properly. For example, if you run, like, let's say, layer 2 VPNs between different sites, in theory, the theory allows such that if you can permit it over the internet and you have some kind of, like, let's say, layer 2 VPN, that can work. But it's not usually commonly suggested to do those kind of things. Usually you try and contain one OSPF domain within inside one logical location. So maybe that's a campus, maybe that's a single building. It all depends on your use case, but there's nothing stopping you from implementing it more wider. As I mentioned, in general, it provides that reachability from one endpoint to another endpoint within a logical network. It's not suggested between different locations or different companies, but it can be, depending on the other protocols that you run with it. It can be used at DC level, and it usually is data center level, but obviously with the caveat that you use a lot of other protocols with it to make sure that it works and make sure that it runs properly. For the likes of BGP, MPLS, or VXLAN. There's a whole other list of protocols that you could run with it as well. So some fundamental concepts. To start off with, routing decisions, they are usually based on a link cost basis. And that link cost basis is based on bandwidth of those specific links. So the links between, sorry, let me get my pointer. The links between these two devices, for example, if that's a 1 gig link, and then you've got a reference bandwidth of 1 gig, the cost there should be 1 gig. And so, as I mentioned, that all comes back down to the reference value, reference bandwidth that you set across the OSPF domain. And that usually is supposed to be static across your OSPF domain. You shouldn't have differing values of that reference bandwidth. And as it mentions here, the reference bandwidth should reflect the best link in the network. So for example, if you have an aggregation point up to your border network and that's running, like, let's say 10 gig, you can set that reference bandwidth to be 10 gig, and then that should reflect nicely throughout the rest of the network. So where you've got 100 meg links, they won't be considered as equal as 10 gig links. The caveat there, though, is that, let's say in that situation where you do have 100 meg links and 10 gig links in the same OSPF domain, if you set your reference value to be 100 meg, all of those links will be considered the same. They'll all have a cost of 1. So while doing the actual logical mathematical calculation of 100 meg divided by 10 gig would give you a decimal point value. What OSPF actually does in the background is it just defaults to 1, where the link bandwidth is higher than the reference bandwidth. So that's something to take into consideration. Sadly, OSPF isn't based on latency or reliability or load, but if you wanted to consider something like load, you could run, let's say, you could run MPLS on the top, and you could run something like RSVP or and the traffic engineering attributes there as well to be able to load balance there based on the actual load of those links. But in OSPF, we can't consider those things. And I mention that because when you look at things like EIGRP, that does actually have the ability to take those into consideration. Whether they are enabled by default is a different matter, but they are there that can be considered. So then when we actually decide on the path that we want to take, it is usually based on a whole knowledge of the OSPF network. And so that OSPF network is can be broken down into separate chunks, and those chunks are identified as link state advertisements. So you have different types of link state advertisements. Each type contains different portions of information. And I'll get onto LSAs or link state advertisements a little bit later, but all of those are stored in what's called a link state database. And you have one link state database per device per area. So where we have here, and this goes on nicely onto areas, where we have here a device which is bordering on one area and another area, that device itself will have 2 link state databases, one for area 0, one for area 20. So you can keep that state separated. And so then, yes, areas. So the concept of areas allows us to basically slightly summarize and limit that LSDB or link state database size. So when we start to look at the LSAs, we'll see that there is a type 1, which describes a router. And that type 1 isn't advertised into area 20, for example. And that type 1 is a relatively large LSA. So by reducing that that piece of information that goes into separate areas, we then can reduce the requirements of one of these devices within inside the OSPF area. So let's say this can be our backbone of our network. These can be fancy, big, high-end devices, while these can be poxy end-of-life devices, and they don't need to necessarily have the highest amounts of memory or RAM or CPU to manage the OSPF domain. However, if they were all within inside one single area and it was a big OSPF topology, those poxy old devices might struggle to actually manage the amount of traffic, well, not traffic, but the amount of information and control messages that it has to process. So that's one benefit there. You can also slightly control the route propagations and the information that you pass on between those two areas. There isn't a huge amount of control. So if you compared it to the level of control that you get in the likes of BGP, where you can control all the way down to every single attribute of a prefix and block or permit whether you're going to advertise them, for example, in OSPF, there's less control there, but you do have a little bit of control on where you want to summarize, if you want to summarize, if you want certain routes going in there, certain types of routes, I should say, going in there. And finally, one rule that is important to take into consideration, why I've used this, why I've created this diagram here, is that all areas should connect back to the backbone area of 0. There are ways to get around it, and I will talk about that in a later talk. But in theory, this area 30 and these devices here won't have any knowledge of area 0 or area 10 networks. If I recall correctly, however, though, they will have details of area 20, but don't quote me on that. but in theory, this is not a supported design. There is a way to get around it. There's a thing called virtual links, and I'll get onto those in a different talk. But if you remember the theory that every area should point back to backbone area 0, then you'll be fine. So the adjacency process, and I won't go into too much detail, but there is a good adjacency detail, and all of these details are documented within inside a pretty self-explanatory RFC. That you've got a lot of detail there if you wanted, but at the same time, it is in some cases high level where you can actually read it and not get put to sleep, basically. So in theory, what will happen is we'll send hello messages to identify ourselves, ourselves being the router, and we highlight our router IDs and certain parameters. And there's some parameters that have to match before you form those adjacencies. So for example, you need the subnet on the interface to be the same, hello and dead timers to match, unique router IDs, interfaces with inside the same areas, and I'll get onto a little bit more about areas later, as I said, and security authentications must match between the two. I have mentioned here matching MTU. In theory, it isn't checked, but it is something highly recommended because when you get down onto these exchange states down here, in larger networks, what you can see is that those exchange packets will be a full MTU size. So if you have a full MTU size and you have, let's say, on R2 a high MTU than R1, when it hits R1, it's either going to cut it down slightly and you're going to miss some of those informations from those exchanges, or you're just going to drop the packet. And obviously that's going to then get you stuck here and you won't be able to go into a full state because you won't have all of the information. That's one thing I think I missed, sorry, that the concept of this link state database is that it is consistent with inside one area. So this device here will have, or should have, the same link state database as this device here. And that's the whole concept of the link state portion of the protocol, is that every device, independent of every other device, should have the same amount of information. So then when you go to calculate a path, you can then do so with the best knowledge. You're not then relying on some other device to interpret it correctly and pass it on correctly. You are relying on just yourself. Now, obviously, that breaks a little bit when you go into areas, but that's a fundamental thing as well. Sorry, I forgot to mention that earlier. So then the process in general, as I mentioned, you send hello messages, and once a device receives those hello messages that you're sending, it evaluates those parameters and says, okay, yes or no, they're good, they're bad. And if they're good, well, then you have a field which is I think it's seen, it could be something else, which basically identifies the router IDs that this device has seen, or its neighbors, I think it is the technical term. Once then you as a sending device see a hello back from your neighbor, you can then send out that hello again, yet again, checking the parameters and identifying that remote device router ID. That, in a sense, is you can think of it as a TCP handshake, SYN, SYN-ACK, ACK, effectively. And it's doing the same kind of things. It's checking those parameters, making sure everything's going to be okay with this session establishment. And I'll mention that a little bit later on, but it basically, OSPF only uses IP. It doesn't use TCP, it doesn't use UTP. It uses its own protocol that sits on top of the IP layer. So it doesn't rely on the controlled nature of TCP to send those control messages. So it has to build in this complexity within the protocol to make sure that any messages are sent are actually received properly or acknowledged in some sense. We then do a bit of a DR election, and I'll talk about what that means in the next slide. Once we've done that, we then start to exchange the database, sorry. And what we do at that point is we exchange database descriptor packets. And to start off with, both devices think they're primary devices. And from that, we identify a primary and a secondary device. There isn't too much reason why we do that. It's just so that one device is leading the communications and dictating when to send and not to send, basically. So we start that election, and then once we've done that, we then fully exchange what's called a DBD packet. And now, so those DBD packets contain LSA headers. LSAs, as I said, I'll get onto a little bit later on, but they basically identify all of the unique parameters for a specific link state advertisement. So once we start obviously exchanging those database descriptors, so those descriptors basically explain or give a summary information of the LSAs. And they do that in such a sense that they remove all the technical detail, but while retaining enough detail to uniquely identify any LSA within inside a network. And so once you actually have those headers, you can then review your internal LSDB and say, yes, I have that one, ignore it. No, I don't have that one. At that point, we use an LSR, a link state request, which can then say, okay, I don't have this LSA. Here's the header for it. Can you send me that specific LSA? And that's what the LSR does, the link state request does. When the R2 device receives that, it will say, okay, happy days. I'm going to send back an LSU, which is a link state update. And that link state update includes the list of LSAs that you've requested. So in that sense, you've requested based on the headers, and then you send back the actual update with all of the full detail of the LSAs. Now, because we're not running with TCP, we then have to acknowledge it. So we send back an LSAC with the full detail of the LSA again, just to confirm that you've received it. Once you've obviously gone through the whole process and you've transferred many hundreds or thousands or tens of database descriptor packets, you can then move into a full state, and it's at that point when you start then stepping through the path calculation process to identify how to get to those remote networks. Okay, as I mentioned before, we had this DR election here. So if you're not familiar with that, what basically happens is when we have these kind of multi-access networks, and multi-access networks could be you just plugging into a switch, a dumb layer 2 switch, and then plugging 10 routers off that single switch, for example. When you have that, you need to identify a single kind of centralized node in the middle. You can imagine like a virtual node in the middle that each one of these devices we will form an adjacency towards. And now we do that because it will reduce the amount of control messages that go over this multi-access network. So in this situation, I've only drawn 3 or 4 devices here, but you could imagine this as, let's say, hundreds of devices off the same layer 2 network. And in that case, what would happen is this device would form an adjacency with all of those 100 devices. In this case, it's only 3 other devices. And when it needs to send out an update, well, it will send out an update to each one of its neighbors. In a sense, sending out 3 updates instead of 1. So you can imagine if you had, let's say, 100 devices off here, you would then get 100 unique updates to each one of those destination devices. Instead, what we do is we have the concept of a DR and a BDR, so a designated router and a backup designated router. So these devices basically form those adjacencies with those DR routers. You advertise then your updates towards those designated routers using multicast. And the DR then forwards out the updates. The BDR sits in the background saying, it's basically a backup, and it stores basically an active state ready to go if the DR fails in some sense. Now, those DRs are elected based on a priority. So, and a priority list is highlighted here. So priority 0, that is ignored. We then go to the highest priority device, which will be this one in this situation. And then if we're tied, which would be the case for when we are electing the BDR, we then go and select the one with the highest router ID just to tie break it. And so the reason why we have those priority values is, yet again, if we have a proxy device in there that can't handle a lot of traffic, can't handle a lot of processing, we can then just set that device to, let's say, have a priority of 0, and then it's just ignored from the election and it doesn't take that load. Now, one thing to note, those elections aren't preemptive. So let's say these top 3 devices come online at the same time. 20 minutes goes by and then this device comes online. Until these 2 devices, one of them goes down, this device will still stay in the DR other state, or it won't be a DR or BDR basically, until one of these devices dies. Whether that's the DR, whether that's the BDR, it doesn't matter. But once one of those is lost, the election starts again. And in theory, the BDR should take over from the DR, or the DR will continue and you just elect a new BDR if the BDR has died. But there is some theory which says that, if you have had this situation where, 3 devices, for example, comes online by themselves, elect, and then new devices come on later, well, then this device could take over if there was another election. Now, if that happens, this device then needs to get all the new state from these other devices, which isn't the best situation to be in. But it's something to take into consideration. Area overview. So as I mentioned, we were talking about areas a little bit. Quick summary again, all areas need to connect back into area 0 as a general principle. There is a way around it, but we'll talk about that a little bit later on. These area numbers, they are 32-bit values, and usually they're just identified by this normal numerical value. But in some instances, they can be referenced as a IPv4 kind of style number. So if you look at a Juniper configuration, for example, you'll often see the OSPF area ID identified in a normal like IPv4 standard addressed kind of style. So once you've obviously set those area IDs, you then assign interfaces to the relevant areas. So this is why when I have this diagram here, these 2 different areas kind of merge on this device here. And so that's happening because this interface on this device is with inside area 20, but then this interface here is with inside area 0. And what that means is this then becomes an area border router because it's bordering 2 different areas. At that point, then you start spinning up a secondary link state database, and you start doing a few other functions that are related to being an area border router. We'll talk a little bit more about that with the link state database, with the link state advertisements in the next slide, but just remember that would become an area border router. You then also have a function that is called an ASBR. So this is an example of an ASBR. So you have a BGP domain, and that is connected to a device which is already inside the OSPF domain. And so when this device redistributes that BGP routing information into an OSPF domain, it then gets classified as an ASBR, or an autonomous system border router. Autonomous systems effectively identifying as a logical grouping of networks. In this case, it's the OSPF domain connecting into a BGP domain. So yes, this would become an ASBR, and that would be highlighted in one of the LSAs that we send out. Flow of routing information. As I mentioned, there are LSAs inside a network, and apologies, I've added some little extra details onto my diagram just as I was reviewing the presentation just a few minutes ago. But in theory, as I mentioned, we have LSAs that are generated by every device. And there's different types of LSAs. This isn't an extensive list. I think there's 15 or 20 different LSAs. I could be wrong. The most relevant ones are the type 1 to 5. There's also a type 7, which I'll briefly mention. But these are the fundamental ones. Without these 5, OSPF wouldn't work. And so, as I mentioned, the LSAs basically are the way that you I kind of like the building blocks for OSPF. They define and they describe the OSPF network and allow a router to actually identify the relevant path. So when it starts to do the path calculation, if it doesn't have all the relevant LSAs, it can't make the right path selection. So when we actually have the LSAs, we have a type 1. That type 1 describes the router and its connected networks. And also the costs associated with them, and some of the attributes related to the relevant device. We then also have a network LSA that's relevant to the multi-access networks, and it describes all the routers that are connected. It's used by the DR and it's generated by the DR to identify, in effect, if it is this virtual node in the middle, it identifies the connections that it has to the other routers that we have there. We then also have a network summary as a type 3. So just logically talking through this diagram over here, let's say we have a subnet that is in here in area 20, this one here. This device here will know about this subnet because obviously it's locally connected. As a result, it'll populate its own type 1 generated LSA for its own device with that connected network and a cost to reach that. Now, because type 1s are advertised only with inside one area, all of these three devices that it is connected, well, these two devices that it's connected to will know about that type 1 LSA and will know how to route towards that subnet. But then if you go into area 0 or if you go into area 10, then you don't have that type 1 LSA, and so you don't know how to reach that relevant subnet. So this is where the type 3 comes into play. So it's generated by an area border router to actually describe the way on how you can reach that relevant subnet. So this device will generate one for this connected network, and it will identify the cost to that given remote network. So in this case, it'll calculate the path to this device, and then it'll add on the cost that's identified in the type 1. From there, then it will get advertised into area 0, and then from there, it will get advertised back into area 10. Maybe I'm going too deep into this, but it is a fundamental for OSPF because without these, the devices won't be able to communicate. They won't be able to path select, basically. Skipping for a section, for a second, we then got type 5, and type 5s are then used when we actually have this redistribution from an external routing protocol. So where we've got an ASBR, this ASBR generates the type 5 to describe the external route. There's a few parameters there, including types of metric and the metric itself. And so that's redistributed throughout the network. And it identifies itself and its own router ID as the originating source for that type 5. So that's fine with inside area 10. So this device, for example, here, will receive a type 5 generated by this device. And it will say, okay, I know how to reach that because it's sourced from this router ID. That router ID then references a type 1 LSA, and that type 1 LSA is what contains all of the relevant information to reach that router ID. And from that, you can then path select because you've got the cost of the links with inside the type 1s, and happy days. But once you're outside of your local area where your ASBR is, you then don't know how to reach the router ID of the ASBR because you don't have the type 1s to reach that. So instead, what we have and what is generated by every ABR is an ASBR summary to identify the cost within inside the local area to that relevant ASBR. So take this device, for example. It knows that there's an ASBR within inside the network, and it generates the cost to that relevant ASPR and advertises that as an advertisement to area 0. Type 7 is then just a similar type 5, which is then used for a specific type of area. I won't get into that too much into detail because it does get a little bit complicated. Finally, path selection. Now, path selection, as some of you might know, is based on Dijkstra's algorithm. I am not the best person to explain that. There is a fantastic explanation by the channel Computer File on YouTube. I'll provide you guys the presentation, and I'll also provide you the link here specifically. It's a really good watch. It's about 10-15 minutes, I think, but they go through it really in detail, how it works, how it hops through everything. So I won't go into too much detail. But the idea is that, you know, if you're on router 1, for example, you know all of the network, so you can start to identify, okay, you want to get to router 5 because you know the network that you're interested in is connected to router 5. So how can we get to router 5? Well, 3 is connected to 5, so what's the cost from 3 to 5, so on and so forth. You select the path as you go based on the cost. And as we mentioned earlier, that is based on the reference bandwidth. So you've got an interface bandwidth, let's say 1 gig, 100 meg, and then you've got a reference bandwidth. That reference bandwidth should be consistent across the whole OSPF topology. If it isn't, then you can start to get conflicting information, which then starts to cause you bugs and issues with the OSPF. But otherwise, keep it standard, keep it consistent across the network, and it should be fine. So what you do to get the cost is you divide the reference bandwidth by the interface bandwidth, and then you get the cost. Now, if the interface bandwidth, as I was mentioning, is higher than that reference bandwidth, the cost will still be 1. So if you have a reference bandwidth of 1 gig, but then you have a mix of 10, 100, 200 gig links, they will all be classed as 1, and then they won't be considered properly. So it's important to get that reference bandwidth correct. One other thing to take into consideration is intra-areas. Area paths are preferred over inter-area paths. What that means is these kind of paths with inside an internal area are preferred over the inter-area connections that we have. So if you take the path from 2 to this BGP redistributed route, while it looks like this is a good path because it's got a low cost, actually 2 won't even consider this because this route is available within inside its own area. So we would never pass through area 1 in this situation. It looks like a bit of a weird topology, but it's technically valid, but we would never pass any traffic between this thing, technically. So that is an introduction to OSPF.